In this short lecture video, we'll talk about trigonometric functions, how they relate to each other, and their usefulness within the scope of trigonometry as a class. There are three basic trig functions that you need to know: cosine, sine, and tangent. Tangent is dictated by sine and cosine, being that it is sine divided by cosine. Cosine always refers to in math as the x value in the ordered pair of the unit circle, or the adjacent side to the triangle if you're multiplying it by the hypotenuse. Similarly, or inversely, sine refers to the y value. There are many types of trig identities that come with these functions that are very useful when doing upper level math questions that require some substitution, or just properties that may only be solved if you understand some of these trig identities. So we'll go over them right now. So some of the basic ones that you should be familiar with just refer to how sine, cosine, and tangent relate to each other and their inverses. So 1 over sine gives us another type of trig function called cosecant. 1 over cosine gives us another trig function called secant. And then 1 over tangent is cotangent. These three trig functions are useful and used only in the sense that you might want to express this as just one type of trig function. So these definitions are useful when they give you problems just as cosecant and you're trying to evaluate it. So it might be easier to just write it in tangent or as sine. Same with secant and cosine and cotangent and tangent. Because this is just how they do it in math classes. If they give you one of these things, it might be easier to re-express it in the other term to actually evaluate it. Similarly, if you just do some algebra, sine is 1 over cosecant, cosine is 1 over secant, and tangent is 1 over cotangent. Very, very similar, very back and forth. I would say if you could just memorize one of these stacks and be able to go back and forth, then you're golden. Over here is more of the same of what we've been saying. Sine refers to the opposite side of a triangle over the hypotenuse. This is the opposite side of the triangle. The opposite side of the triangle is always perpendicular to like the incident angle. So like the incident angle is made like right here. And whatever side has whatever side has like the 90-degree right angle is on the opposite side. This always refers to the adjacent side, conversely. Once you have identified the opposite and adjacent side, the hypotenuse is always quite obvious, and then you can evaluate any one of these trig functions by doing opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, yada, yada, yada. So being able to comfortably navigate these inverse definitions and how they relate to the sides of a triangle will be very useful and important throughout your math career, I guess. So in this example, we will be tasked with finding tangent of pi over 6. Now, on the unit circle, I don't always remember what tangent is, but I do, and hopefully you too, remember what sine and cosine are on the unit circle. If we can locate exactly where it is on the unit circle, know what the sine and cosine values are, then we can figure out what tangent theta is. Pretty, not too bad. So pi over 6 is the first angle on the unit circle. So it would be literally the first angle right here. What do I know about that angle? I know that it's the first values above 1, 0. So it has a larger x value and a smaller y value. And if you recall, the x value or the values for all the trig functions on the unit circle just go as 1, 3, root 3 over 2, root 2 over 2, 1/2, and then again with 1. That's just cycling through all the values, and they just flip versus which x value is larger and which y value is larger. So right here on the first angle, we have a larger x value and a smaller y value of, compared between these three other radians. Therefore, I'll recall that cosine of pi over 6 is, since it's the larger value, is equal to root 3 over 2. And for sine, it would be 1/2. Because right here, this ordered pair is root 3 over 2 and 1/2. Okay, so now that I know the sine and cosine values, I'll refer back to my definition for tangent, which I know is sine over cosine. So tangent of pi over 6 is going to be 1/2 divided by root 3 over 2, which would be the same thing as like multiplying by 2 over root 3. These twos cancel out. So now my answer right here is 1 over root 3. Not too bad. Again, this is kind of an unfortunate time in math where you really just have to learn a pattern and be able to apply that pattern. So the pattern that I remember for like a unit circle goes as pi over 6, pi over 4, pi over 3, and then that's in its first quadrant. X value is larger on the lower angle, which gives me root 3 over 2 and 1/2. Then you have 45 degrees, which is root 2 over 2 for both of them because it's evenly between the x and y value. And then for the top angle, it just flips. So now the cosine value is 1/2 and the sine value is root 3 over 2. And then after you just know that, then all the other angles come from just knowing what quadrant you're in, whether it's positive or negative. But after that, everything else is gravy. So some very important trig identities. Throughout trig, you are probably going to be introduced to more than just these, but for the grand scope of mathematics, these are more or less the most important ones. This one by far is something that you should or just will eventually memorize. Sine squared plus cosine squared is equal to 1. This is very useful in other mathematics when you have to do substitutions for higher level algebra, when you can't finish it with normal algebra and you have to do a substitution to make it easier. These trig identities also help you find values to these angles when you don't know enough about the angle that's involved, especially if the angle is not a unit circle angle, like not something that you should know or something that like you would know or can evaluate off the top of your head, then it's pertinent to like use these trig identities to try and help you get an answer. The other two here, this one's also widely used. The way I typically see it written, or the way I would like to write it, is tangent squared is equal to secant squared minus 1. Because I feel like most of the time when I've ever had to use that identity, I'm usually like replacing tangent squared or secant squared with something. But either way, this is still this is still the right answer. So right here, we can actually do one of these examples to help test our knowledge of our trig identities. So let's just take the first one. Prove that tangent theta plus cotangent theta is equal to secant theta plus cosecant theta. So what do I know about tangent and cotangent? Well, I know tangent is the same thing as sine theta over cosine theta. And I know cotangent is the opposite of that, being cosine theta over sine theta. Now, if I just do some simple algebra, multiplying the sine theta to the top and bottom of this one and cosine theta to the top and bottom of this one, so I can have like denominators and then combine them, I'll get sine squared theta plus cosine squared theta over cosine theta times sine theta. Now, using this trig identity up here that we all memorize in Lev, I'm going to rewrite this as 1 over cosine theta times sine theta. From here, you should be able to already recognize that we're pretty much done. Since it's a 1 on the top, I could rewrite this thing as 1 over cosine theta multiplied by 1 over sine theta. And then this right here is equal to secant theta, cosecant theta. Now that you've kind of got an idea of how trig identities can relate when doing or evaluating trig problems, I would task you to try and prove these other examples, solve or prove these other examples using these trig identities. It would fall very similar with the method that we just did. So for instance, if I was going to start with number 3, doing cosine and cotangent, I'd first write cosine times and value and like expand cotangent. So I'd have cosine times cosine over sine, and then work forward from there doing algebra until you can get something simpler, and eventually you would end up with something like this. So is the method for most trig forms. Trig problems are examples where they ask you to prove something.